Swayam Prabha. Digital India. Educated India.
Welcome to the next session on the Organic Chemistry Paper 2. The fourth module is about alkyl halide reactions. In the lecture 2, we will be studying about elimination reaction E1 mechanism. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. So in this session, the topics that we will be studying include E1 mechanism and the evidences which favor the E1 mechanism, and we will also be studying about the comparison between elimination 1 and elimination 2, that is unimolecular and bimolecular elimination reactions, and the comparison between substitution and elimination reactions. Let us continue with our elimination reactions of alkyl halides. This time we will look at E1 mechanism. So in the E1 mechanism, the reactions are very similar to SN1 mechanism where a carbocation is involved. So in the first step, the halide is removed to form like X minus and the carbocation is formed. This is a slow step or the rate determining step. Then the base abstracts a proton and the bonded electron is shifted between the carbocation carbon and this carbon to give the alkene. HB is removed. Generally the proton abstraction is always a fast step, so that's the reason the second reaction is a very fast one. The carbocation actually attains the octet configuration through the electron donated by the loss of the proton, that is the beta hydrogen. So these carbocations are generally 6 electron species. So this bonded electron is coming between these two carbons to make the electronic configuration of this carbon as 8. So what are the changes taking place in this particular reaction, that's carbocations? So the carbocation can combine with the nucleophile. So if it combines with the nucleophile, then that is very similar to a SN1 mechanism or SN1 reaction. It can undergo rearrangement to a more stable carbocation, so that we had seen even in the case of SN1 reaction. But elimination of a proton to form an alkene, so this is what is the difference from the SN1 reaction. So here the elimination of the proton takes place, and for this particular reaction the rate is the concentration of the alkyl halide is the one which is involved in the rate law. In other words, the first step was the slow step. The formation of the carbocation was the slow step, so that's the reason we say the rate depends only on the concentration of the alkyl halide. Let us look at some of the evidences for the E1 mechanism. So it follows the first order kinetics. According to the rate law, the concentration depends only on the alkyl halides. And the second one, rearrangements are possible because carbocation can undergo rearrangement. Then the effect of the structure on reactivity and no primary hydrogen isotope effect is involved, because in the rate determining step, CH bond is not broken like the E2 mechanism. So that's the reason there is no primary hydrogen isotope effect in this particular mechanism. Because what is the first step in this reaction? The first step is nothing but the elimination of the alkyl halide, elimination of the halogen to form the carbocation. Let us look at a couple of examples. So in this particular case, we have a halide on this particular carbon. This is the alpha carbon and this is the beta carbon. So in this beta carbon, if you look very carefully, we have a methyl group, we have a methyl group, we have a methyl group. So that means there is no hydrogen on the beta carbon this side. Of course, this side we have 3 hydrogens on the beta carbon. This is example number 1. Let us see how this undergoes elimination. So if only these beta hydrogens are involved, then we will only end up with the product which is this one, because elimination can only happen from the terminal. This is the terminal carbon, so the terminal alkene only is possible. The internal alkene is not at all possible. So how does this actually happen? This happens because of the rearrangement. So this is one of the proof to show that this reaction proceeds via rearrangement. And let us take about the another case. So we have a alpha carbon here and we have a beta carbon here. So this alpha carbon, the halogen is present on this alpha carbon. So here if you look at, we have a methyl group, another methyl group, another methyl group. So this substrate does not even have any beta hydrogen. So that means there is no beta hydrogen for this particular substrate. Even then this undergoes elimination to give 2 alkenes. So how these are possible? These are possible only if there is a rearrangement possible. That means the carbocation, in the first step the carbocation has to form. So the alpha carbon will become the carbocation, and then there is a shift of the methyl group from this carbon to this carbon takes place. So when that happens, which we had actually seen in the SN1 mechanism also, the same type of carbocation rearrangement also occurs here. So that proves that even mechanism, the carbocation undergoes rearrangement. And when we look at the reactivity, the tertiary reacts faster compared to secondary, which in turn reacts faster than the primary, because the reactivity is basically determined by the rate of formation of carbocation. So we already know tertiary forms the carbocation much faster. So that's the reason the rate also depends on the reactivity also depends on the rate of formation of the carbocation. And we also know the stability of the carbocation. The tertiary carbocation is more stable compared to the other 2 primary and secondary carbocations. And in this particular case, we do not have any kinetic isotope effect, because in the rate determining step, the CH bond is not broken. So that is the reason there is no isotopic effect in this particular case. And when we talk about orientation of E1 mechanism, this also follows the Zaitsev rule as we had seen in the E2 mechanism. So the more stable alkane is the preferred one, that is the highly branched one is the most preferred one according to Zaitsev rule. And example is given here. So we have a alkyl halide undergoing elimination reaction to produce 82% of one isomer and 18% of another isomer. So this is the more branched one. We have branch number 1, 2 and 3 branching is here. In this particular case we have 1 and 2. So that means this is the most branched one. So this is formed in large excess. So this is what is the orientation, and reactivity is basically determined by the relative rate. So we know the step 2, which is the olefin formation, the orientation leads to the step 2. And when we talk about orientation is the product formation basically. And when we say reactivity, it is the how quickly the carbocation is formed. So these two are the two different things. So the first one, the reactivity leads to carbocation formation, and in the orientation we end up with a stable product. So these are all the two things we have to remember when we talk about E1 mechanism. And we have a substrate, the carbocation. Here you see the carbocation is in the central carbon, and we have carbon number 1, carbon number 3. So this is actually formed from OTS. Of course, Bromine can be converted to OTS. OTS is a much better leaving group compared to halides. So whatever is applicable for OTS in this particular case is also applicable for halides also. So the carbocation can give a minus isomer if it undergoes elimination from this side, from the carbon number 1, and it forms the major isomer if the elimination occurs from this side. So this is how we can say the orientation of the final product. And when we talk about the transition state mechanism, so in this particular case what happens is, in the transition state, the base combines with the hydrogen atom, and this bond, the CH bond, is weakened, and simultaneously the CC bond is partially formed because we have a delta plus charge on this carbon. So when the CH bond is completely broken, this bonded pair shifts between carbon and carbon to give the final alkene. So as we mentioned earlier, any factor that can stabilize that alkene also stabilizes the transition state. So that means any factor that lowers the E energy of activation actually favors the fast product formation. So these are all the two things which are, one is related to thermodynamics. Thermodynamics means stability of the product. Another one relates to kinetics of the product. That is, energy of activation is for the kinetics, how fast the reaction proceeds. So that is mentioned by this energy of activation, and how stable the product is formed is mentioned by the thermodynamics of the reaction. So we study both kinetics and thermodynamics of these reactions. And let us compare the elimination of E2 versus E1. So here we can study about the effect of alkyl groups on the structures. That is, how bulky or how small the alkyl groups determine what is the outcome of this particular reaction. So when we talk about the primary, this is a very small or linear group. So according to E2 mechanism, the primary is having a less branching, so this reacts. This reacts much faster compared to tertiary, that is because there is a more branching in this particular case. Whereas in the case of E1 mechanism, the primary carbocation is less stable, whereas tertiary carbocation is more stable. So the tertiary reacts much better by E1 mechanism. And when we talk about nature and amount of the base, in the E2 mechanism, the base is involved in the rate determining step, so a stronger base is essential for the E2 elimination. In the case of E1 elimination, the base concentration is not involved in the rate determining step, so the strength of the base does not affect the E1 mechanism. So that's the reason we can say the E2 depends on the concentration and the nature of the base. That means higher concentration and a stronger base generally favors E2 mechanism. And when we compare the elimination with the substitution, so we have two things. That means Z is either can be called as a nucleophile or a base, because both are negatively charged or neutral species having electron rich. So we had already seen the comparison between nucleophile and the base. So they both do the more or less a similar job. The base generally abstracts a proton, whereas the nucleophile adds to the carbon or the substrate. So this is the major difference between base and the nucleophile. So here when we talk about S, that means substitution means the nucleophile adds to the carbon. When we talk about elimination, the nucleophile or the base removes the proton. So this is the major difference between elimination and substitution. So when we talk about the order of reactivity, in the case of E2 elimination, tertiary reacts much faster compared to primary, whereas in the case of SN2 reaction, the tertiary reacts very slow compared to primary. So in the case of primary, it undergoes very slow elimination or it undergoes fast substitution. That is when a bimolecular elimination or substitution is concerned. So when we talk about SN2 or E2, the primary undergoes very slow elimination by E2 mechanism, or it undergoes very fast substitution by SN2 mechanism. And the proportion of this, basically the elimination increases as the substrate structure of the substrate changes from primary to secondary to tertiary. So in the case of alkyl halide, the primary favors substitution and the tertiary favors elimination in E2 mechanism. Because that is what we are studying here, E2 versus SN2. And with a less polar solvent and high temperature basically favors elimination. So if you have an alkyl halide, KOH or water at room temperature generally leads to substitution. The Br is replaced by OH. So this happens at room temperature. But when we use base and heating, this leads to elimination reaction. So this is the difference between the solvent and the high temperature. And basically a good nucleophile favors substitution, whereas a weak base favors substitution. So we will study some mnemonic about how to remember all this. And when we come to SN1 versus E1, the alkyl halide undergoes the formation of the carbocation. So this is the first step. Then the nucleophile attacks. So if the nucleophile adds, then that becomes SN1 reaction. If it is a base and it removes a proton from the carbocation, then we get the alkene. So that is what is called the E1 reaction. So we can confirm that is that the nucleophile attacks the carbocation, gives the substitution. If the base attacks the beta hydrogen, then we get elimination. So here again, whether the Z or the nucleophile or the base abstracts a proton, that becomes elimination. If it adds to the carbocation, that becomes substitution. So the rate of elimination is basically tertiary undergoes elimination much faster compared to primary. In substitution, primary undergoes reaction faster than the tertiary. For the tertiary, elimination is always preferred. So in this particular case, low or less polar solvent and a stronger nucleophile or high concentration of the base favors bimolecular elimination. Let us do a comparison between SN2 and E2. So that means in the case of primary alkyl halide, SN2 is the favored because there is no steric hindrance on the alkyl halide and nucleophile. And it also undergoes E2 when there is steric hindrance. So when there is no steric hindrance, it prefers SN2, but there is steric hindrance, it follows E2 mechanism. And in the case of secondary alkyl halides, it generally follows reaction by SN2 mechanism. And if it undergoes E2 mechanism, then we do need a strong and bulkier base. So only then it undergoes elimination mechanism. And the tertiary alkyl halide does not undergo SN2, it only undergoes elimination reaction. So in the tertiary alkyl halide, we do not talk about SN2. And the comparison between nucleophilic substitution and elimination, we can say the bimolecular reaction, primary reacts faster compared to tertiary. In the case of E2 elimination or SN1 and E1 mechanism, in both the cases tertiary reacts faster than the primary one. So in other words, what we can say is strong bases favor E2 reaction, non-polar solvents favor E2 reaction, and high temperature also favors E2 reactions. So this again you can actually go through that. When we talk about a nucleophile, a strong nucleophile favors SN2 reaction, a strong base or a bulky base favors E2 reaction in the case of primary alkyl halides. And in the case of secondary, a strong base and a nucleophile basically favors both the reactions SN2 and E2. So that is why the secondary reactions, secondary alkyl halide reactions are more complicated than the primary or secondary, because they can undergo reaction both by SN1 mechanism and SN2 mechanism. If you look at here, we have SN1 and SN2. So basically, based on whether we have a strong nucleophile or a weak nucleophile, they can undergo reactions by different mechanisms. And in the case of tertiary, we do not have a SN2 mechanism, we only have SN1 mechanism, or the type of reaction is only SN1. If we use a very strong base, it undergoes reaction by E2 elimination. So how you can remember all these things is a mnemonics which you can actually follow. I'm new to BSc. BSc is nothing but a stock exchange, if you can remember that. So what is this new to BSc? So new means, what is this NEW? N is nucleophile, E is elimination, W is weak. So when we have a weak nucleophile, it favors elimination reaction. When the base is strong, B for base, S for strong, that favors elimination reaction. So put together what we can say, a weak nucleophile or a strong base favors elimination reaction. And on the contrary, you can also remember the second one. I went to WBS, to NSS trip. That means West Bengal state, I went for NSS trip. So this is another things which you can remember like a mnemonics. So W here is a weak, B is a base, S is a substitution. So that means weak base favors substitution reaction. And NSS trip, if you remember, though N is for nucleophile, S is for substitution, S is for strong. So you have a strong nucleophile that favors substitution reaction. So by remembering these two, you can actually remember the entire SN1 and E1 mechanisms in a much simpler way. Let's recap the summary. We have studied elaborately about the E1 mechanism, and we have studied about the evidences which favor the E1 mechanism, that is the formation of carbocation, and we also studied about the stability, reactivity and rearrangements of various carbocations. And finally, we studied about the comparison between E1 and E2 mechanism and the substitution and elimination reactions, and what are the tips how we can find out which type of reaction mechanism may happen in the alkyl halides. With that, we conclude this particular session. Thank you.